Dear students, in today's lecture we will study about power and torque in induction motors. So first of all, we have a basic circuit diagram of induction machines, and first of all we will consider some losses, power losses, which are uh, experienced in the induction machines, and by deducting these power losses from the input power, we will be able to get the output power, which will be uh, quite less than the input power. So if we see about the main main reasons, which are the reasons for the power losses. First one is copper losses. There would be two types of copper losses. One is stator copper losses, another is rotor copper losses. Similarly, then there is another type of loss, and which is called core losses, and the power losses because of the core losses are shown with P core. Similarly, there are some other losses which are uh, because of the mechanical friction and windage of the machines. So we will consider these losses, and we will come to know that how the final power would be deduced, and it would be finally obtained after reduction of these losses. So in this power flow diagram, it is quite obvious that this is our input power, after which we experience the stator copper loss and core losses. Then PAG, AG stands for air gap. So air gap power is at this point, which is in between the stator and rotor, and after which the rotor losses are also considered. This is P conv. P conv means that it is the point where power has been converted from electrical to mechanical power. So when the power has been converted to mechanical power, after that the mechanical aspects are also considered, which are friction and windage. So P loss because of friction and windage, and P stray, which is miscellaneous power losses. So this is the tau load omega m is the final P out in an induction motor case. So the core losses of an induction motor come from both the stator and rotor circuit. Since an induction motor operates at a speed near to the synchronous speed, the rotor core losses are very small as compared to the stator. So we know that as we increase the speed of an induction machine, since the speed of the induction machine has been increased, the higher speed will experience the higher friction because of the power losses which deals with the mechanical rotation and friction and windage. So in this case uh, it would increase the losses because of friction, windage and stray losses. So the higher the speed of the motor, the lower its core losses. But the core losses would be lower in the case of the higher speed. These losses are sometimes lumped together and called rotational losses. So they mean that these losses can be combined together and called as rotational losses overall. Since the component losses change in opposite directions with a change in speed, the total rotational losses of a motor may be considered constant with the changing speed. So it is quite clear that the component losses, if the components change in opposite direction with the change in speed, the rotational losses may be considered constant with changing speed. Now we see that the I would be equal to voltage over impedance, or we can say equivalent impedance. But from the circuit we come to know that equivalent impedance is equal to this, which is written in purple color, the equation written in purple color. If this is Z equivalent, then the copper losses and the core losses can be obtained from the formula, and we will be able to find the power of air gap. The PAG is equal to the P input power minus the two losses. So the AG power is consumed in R2 over S, as it can be seen from this equation. So we know that resistive losses in the rotor circuit can be given by RCL, PRCL, and when we come to know that if we include these losses, then after stator copper losses, core losses and rotor copper losses are subtracted from P in, the remaining power is converted into mechanical power. So the converted power would be written as P conv. So P conv is basically PAG, which we obtained on last slide. So PAG minus additional PRCL, which now we are considering. So uh, after deducting PRCL from PAG, we will get the converted power. But we know that this converted power would further be deducted to obtain the final power. So if this is the final power, this P con is further deducted with two mechanical related power losses, which are friction and winding and the other miscellaneous power. So this P out would be the output power, and these two further power losses are also considered in this equation. Now we come to know that how can we write the torque, the induced torque in the machine. So we know that tau induced can be written as P converted over omega m, or mechanical speed. But we know that P con can be written in terms of P air gap, or PAG, something like this. And similarly omega m can be written in terms of omega synchronous, then 1 minus s, and this 1 minus s would be cancelled with each other, and we will get a simpler form of torque, which is air gap power over synchronized speed. So some part of the power coming across the air gap in an induction motor is consumed in the rotor copper losses, and the some part of it is converted to mechanical power to drive the motor's shaft. These two parts of PAG can be separately indicated on the motor equivalent circuit. So these are basically the converted power, and this is air gap power. So if these are the relations, by simplifying them we can get that P con is equal to 3 I2 square R2 1 over S minus 1. But we come to know that this equation can be written as 3I square into R. If we see that this is R, then R con can be written as R2 1 minus S over S. So we can say easily that the equivalent circuit can be modeled for these resistance by including them. The two resistances which are included in this case are basically the resistances which are dealing with the mechanical friction or rotor resistance. So resistance 1 R2 is showing the stator side of the rotor resistance, and the R2 1 minus S over S is showing the resistance equivalent to mechanical load. So now we will discuss about some power relations. So these power relations would be mostly used in solving the examples and numericals related to uh, the induction motors, in which we will deal how the power has been lost in the way, and how the power has been converted from one form to another form. So first equation is showing the P in, which is Vi cos theta, 3 Vi cos theta. Then the second equation is showing SCL, which is copper loss. Cl stands for copper loss and S is for the stator, for power stator copper loss. Similarly, power air gap. So power air gap can easily be found out, as we have discussed in previous slide, that if we uh, subtract P SCL and P core from P in, then we will be able to get PAG. And if we further deduct P RCL from PAG, we will get P converted. And from P converted, if we further subtract two other losses, mechanical losses, then we will get the final P out. And these relationships can further simplify like this. Some of these equations can further be simplified. So now we come to an example in which a three-phase induction motor is considered, and in this the specifications of the induction motor are given, and we need to know the four things. One is the PAG, air gap power, P converted, which would be PAG minus 1 power loss. After finding P converted, we want to find P out, which would be P converted minus two other power losses, which are the mechanical power losses. At the end, we want to know the efficiency of the motor, which would be eta, represented with eta, and it can be said that it would be P out over P in. So it's quite easy if we know about the relationship of these power equations. In first part, which is quite easy, we know the value of P in, and after deducting two power losses, power core and stator copper loss, these power losses are deducted from P in to get the P air gap. After finding the P air gap, this is P air gap, if we deduct rotor copper loss from P air gap, we will get the P converted. Now we have calculated the two parts. In third part, the P converted is further deducted with two other powers. In this case, one is friction and winding power, another one is P miscellaneous. In this case, P miscellaneous has been considered negligible. And in third part, we come to know about P out, and in this P out, we know that in fourth part this P out would be used, and we will come to know about the efficiency of the motor, which is equal to P out over P in. So by inserting the values of P out over P in this fourth part, we will come to know that the efficiency of this motor is 88%. Thank you, student.